All right, that's good. Good morning, lads and ladies. Welcome back to Calc 2. Lately, we've been talking about volume problems, how we can find volumes of solids of revolution. Those are solids that are obtained by rotating some two-dimensional region about some fixed axis of rotation. We'll take a quick look at your syllabus to make sure that we've actually captured the bulk of what we want to capture, and then I'll decide exactly how we're gonna portion the time today. So, Maxie, come here. Go ahead and turn on the screen share. We can do it together. Why not? So here we are. This is you guys. And yeah, we still need to talk about work. So let's do that. I take this section very gently. This is not a physics class. If you want to learn a lot about work, go take a physics class. But I'll show you what it is, and we'll solve a problem or two. I think it's probably worthwhile to look at a couple of cylindrical shells problems because we barely touched that. We did one example, I think. So we'll start there, and then we're going to talk about work. The bulk of today, the intent is to kind of just get you a little bit more comfy solving the problems. So let's do that. All the animals are roaming free right now, so I may have to run up and throw one in a pen or something. I apologize in advance if that happens. Where did QCam go? All right. Let's do it. Contrast. So this is MAC2312, section 004, that is Calc 2, and today is the 3rd of September, 2021. Today, we're going to look at some more volume problems. These are sections 6.2 and 6.3. We're going to focus on 6.3. And then we're going to talk about work, which is section 6.4. Okay. Let's start with a volume problem or two. I'm going to pick the first one, and I'm going to grab it from section 6.3 because I want to make sure we've seen at least a couple examples of each method. Before I do that, here is your volumes cheat sheet. All right, this is everything you really need to remember to solve these volume problems. So for all of this stuff, sketch the region. So you sketch the curves, shade the region. And draw the axis of rotation. And then what you do from there depends on which method you're using. For the disc washer method, you draw the strip perpendicular to the axis of rotation. Remember, after doing these things, your next step for both is to draw a little differential thickness strip. And then you need to figure out a few things. Little r will be the distance from the near end of the strip to the axis of rotation. So I'm doing this for you now because I want you to have one place in your notes where you can look and have all the stuff. So please do me and yourself a favor and write this in your notes. Big R is the distance from the far end of the strip to the axis of rotation. And then V will be the integral of dV, where dV is the volume of the little solid you get just by rotating that strip, which is always going to be pi times big R squared minus little r squared. I'm writing dt here because dt could be dx or dy. Depending on the situation, right? So with the disk washer method, you could think about it and be more specific here if you wanted to. Since the strip is perpendicular to the axis of rotation, if you have a vertical axis of rotation with the disk washer method, your strip will be laid in horizontally, which means its thickness will be a little vertical thickness, which means it's going to be a dy. If your axis of rotation is a horizontal line, then your strip will be drawn in vertically, which means its thickness will be a little horizontal thickness, which means dt would be dx. If you want to add that detail, you can. For the shells method, the strip is parallel to the axis of rotation. And then you need to cook up a radius, little r, which is the distance. There is no near or far end with the cylindrical shells method, right? Because the strip is parallel to the axis of rotation. You just go from the strip to the axis. Because that strip is supposed to be differential thickness, right? Like dx or dy thickness. It really is a point thick. And then you have to come up with this quantity h here also, which is the length of the strip. Length or height of the strip. And then v will be equal to the integral of dv, where dv is 2 pi r times the height times dt. And again, dt could be dx or dy. And if you want to get particular about that stuff with this one, you can, just like with the previous. With the cylindrical shells method, since the strip is parallel to the axis of rotation, if the axis of rotation is a vertical line, the strip would be drawn in vertically, which means its thickness is a dx thickness. So a vertical axis of rotation here means you're going to be working dx, and a horizontal axis of rotation for the cylindrical shells method means you'll be working dy. I recommend not memorizing that. This is kind of the minimal amount of shit you can remember and be able to handle all these problems. All right, so this is fully general. These rules always work. It's not like the formulas you're going to find online or elsewhere. Those will not work. And in the vast majority of cases where your axis of rotation is not a coordinate axis or something like that, yeah, these will always work, but it requires a little bit of thinking. Of course, these integrals are definite integrals. They should be definite integrals. Maybe I'll put an a to b here. You have to figure out those bounds. So I'm going to hold here just for a minute. You can take a screenshot or plop this into your notes. Are there any questions about this kind of outline of the two methods? hopefully you see the thing that really differentiates, pardon the pun, one from the other is the orientation of the strip with respect to the axis of rotation. Strip being perpendicular to the axis or the strip being parallel to the axis. That's really what makes these things what they are. All right, let's grab a problem from section 6.3. There's an example problem in here. It's not too bad. The one that involves the sine of the square root of x or something, sine of x big squared. Well, that's in your homework. Let's do something else. Y-axis between. Yeah, okay, let's do this one. In fact, I think I got an email or request about this one the other day. So let's find the volume of the solid obtained by rotating about the y-axis, the region between y equals x and y equals x squared. Again, I'm not going to write all the words. So y equals x. Actually, you know what? Let me change this a little bit. Y equals x squared. X equals. Oh no, that might not work. All right, yeah, we'll work this one as it is. We'll work this one as it is, and then we'll do another one. About the y. These two boundary curves we've used a lot, so I should probably be pretty comfortable drawing this at this point. And I think this exact problem we have worked out using the dishwashing method in the past. Okay, so here's your x-axis, here's your y-axis. We know that this intersection point is 1, 1 in the region. Y equals x squared definitely continues over here, but I'm not going to draw that. And you see that I've zoomed in real close on the interval 0 to 1. Exaggerating that parabola quite a bit. This guy is y equals x. Squared. And my axis of rotation is the y-axis. So regardless of which method I was going to use, this is how it would start. And now, because I'm doing this in section 6.3, I want to use the cylindrical shells method rather than the dishwasher method. And you'll see in some senses, the shells method here is nicer.
How do we know exactly which one to use?
It's a good question. So in general, if the problem just says find the volume and it doesn't specify a method, you're free to use either method you want. Now, lecture logic, kind of as you're working the homework problems, if the problem says 6.2.19 or whatever, 6.2 point something in the problem description, then you want to use the dishwasher method. And if it says 6.3.7 or whatever, it starts with a 6.3, then you should be using the shells method. But out there in the world, if you want to find a volume of a solid like this, then you'll have to pick which method to use. If you set it up with the dishwasher method and the integral looks unpleasant, or you can't set it up with the dishwasher method, then the cylindrical shells method is the way to go. And there isn't a hard and fast rule that I'm aware of that says, you know, under these circumstances, one is always nicer than the other. Beyond what I've shared with you already is that if your boundary curve is not 1-to-1 in that region, like we saw at the end of class yesterday, or sorry, Wednesday, then you'll need to use a method that doesn't require solving that not 1-to-1 function for its independent variable. But I would say just try setting it up both ways. If you're unsure, grab one and try it. And if it doesn't work out, try the other. On the exam, I'll specify the method I want you to use because I'll be looking for very particular things. Okay, so here's my region, the curves, axis of rotation, and I've drawn my strip in parallel to the axis of rotation. So now I imagine rotating just that strip. I know that's going to produce for me a little solid that looks something like this. Doesn't have to be perfect. But you get the idea. Something like that. Remember, this is a shell, right? It's not full. It's like a soup can with the top and bottom popped off. The thickness of this wall here is the thickness of that strip, which is dx. The other dimensions we need are this height and this radius. So the height, remember, is the length of the strip, the length or height of the strip, and the radius of that shell is always the distance from the strip to the axis of rotation. All right, so you're right there. Those are the only little bits of information that I need to remember in order to cook this shit up. On the test, I will require you to sketch the region, sketch the curves, the strip, and to label these distances. All right, the problems will say that specifically, but just giving you a heads up. On the test, you'll be required to produce this picture. You won't be required to produce this picture, but it's not a bad idea to do it, especially for the disk washer method. I find it helpful. But you will be required to do this, to draw the curves, to draw on the strip, and then to label the radius and the height, or in a disk washer method, the 2 radii. Okay. Let's do the height first. Remember, this strip is always drawn in here at like an arbitrary x position, right? Just like a generic x position. So what is that height?
X minus x squared.
Good. It's the y value up here, which is x, because this is the line y equals x, minus the y value down here, which is x squared, because we're along the curve y equals x squared. And my radius, this horizontal distance, that's just x. Which means my little volume, the volume of this shell, when we cut and unroll it, go ahead and draw it just the one more time. The way we cook this up is by taking some very sharp scissors to our soup can, running up the side, and then unrolling. It has a very, very thin wall, which I'll exaggerate here a little bit. And when you do that, and you cut and unroll that thing, you'll get a little box. It's much, much longer than it is wide. It's much, much taller than it is wide, but our pens are only so sharp, right? So this dimension is dx. This dimension is the circumference of the shell, which is 2 pi times the radius. And this dimension is still the height. Okay, well, if the radius is x, then dv is going to be 2 pi x times the height, which is x minus x squared, times that thickness, which is dx. This is just coming from the formula that I gave you at the start of class, right? 2 pi RH. It's okay, it's 2 pi RH times dt. Alrighty, and then to finish things up, my volume is the integral of dv. And this is going to be, everything here is being done with respect to x, because my strip is oriented like this. I'm going to integrate from the smallest x value in my region up to the largest x value in my region. That's from x equals 0 up to x equals 1. So when we plug everything in, I can pop out that 2 pi constant, integral 0 to 1, and then x times x minus x squared dx. Any questions so far? I'd argue that's the bulk of the work. That's the hard part. We're all super comfy with this? Okay. Distributing the x, we get 2 pi integral 0 to 1 x squared minus x cubed. And remember, you have to do that. Can't integrate products nicely, but we can integrate differences nicely. And then we can use the power rule for our antiderivatives. Antiderivative of x squared is x cubed over 3, or 1/3 x cubed. And an antiderivative for x cubed is x to the 4th power divided by 4. And we evaluate that from 0 to 1. If I plug in 0, these are both 0. So the only contribution comes from the upper bound when I plug in 1. And then this will be 1/3 minus 1/4. So this is 2 pi times 1/3 minus 1/4. Common denominator there is 12, so that's 4 minus 3, or 1/12. So it's 2 pi times 1/12, which is pi over 6. So that's the volume of the whole solid. Any questions on the computation, the integral? Okay, let me remind you that there is a place you can go. Oh, did my browser change? It did. I'd just like to show you one more time that visualization where you can go to see that. I do think it's really helpful for building some intuition. We looked at the visualization for the dishwasher method. If you want to see what's going on with shells, come here. I'm going to skip ahead. You can watch the whole thing if you want all the details, but here we go. Here's your region. There's your strip. And if you rotate just that strip, you produce this cylindrical shell. That's the thing whose volume we call dV. And then what the integral does is it adds up all those little volumes over all the possible strips. So if you look at a bunch of strips, right, and what the integral does is it just does that with an infinite number of little shells, infinite number of very, very thin little shells. And that's it. That's how you get your volume. So I invite you guys to watch these if you're having any sort of trouble, especially as you work the homework. If you're getting a little bit stuck, I think it would be a good idea to take a look at those. Okay. We can look at one more volume problem here before we switch to talking about work. And I would like to make it a tricky one. A variation on this problem shows up in your homework. It's not bad. Most of these are a little bit too straightforward. Challenging problem. So number 5 here doesn't look bad. 25 doesn't look bad. The rest of these are too easy because the integrals are all polynomials. Let's do the sine of root x, or sine of x squared. Well, actually, a none. Yeah, I'd like my coordinate axis, my axis of rotation to be something that's a bit weirder. What was this about y equals 4? Let's do 25. Let's do 25. So we're going to find the volume of the solid, blah, blah, blah. One of our curves is x equals the square root of the sine of y, which is certainly a weird curve. We're working y values between 0 and pi. And we're rotating about the non-coordinate axis, x equals -1, right? Or no, sorry, y equals 4. Y equals 4, 25. Okay, I copied down the important information, going back to the dot cam now. First things first, probably you don't know what this graph looks like. I don't know what this graph looks like off the top of my head, but we can figure it out. And then instead of giving us multiple boundary curves, they gave me an interval for y values. It's interesting, that's new. And then our axis of rotation is not the x-axis or the y-axis, it's a different line. So let's start with this. When y is equal to 0, this whole thing here would be the square root of the sine of 0, which is 0. I'm going here, I'm going to start drawing this. All right, so when y is equal to 0, this is my y-axis, x is also equal to 0. So the origin is on that graph. When y is equal to pi over 2, the sine of pi over 2 is 1. This would be the square root of 1, which is 1. So when y is equal to pi over 2, which maybe I'll mark this up here as pi, which makes this right here, pi over 2. When y is equal to pi over 2, x is equal to 1. So maybe if that's pi, I'll say 1 is here. I'll extend it out a little bit. So we've got this point on the curve. And then when y is equal to pi, this is the sine of pi, which is 0 again. And the square root of 0 is 0. So we're coming back here. So my guess is that this curve looks something like this. We can think about it a little bit more critically. As y begins increasing from 0 towards pi over 2, the sine function does begin increasing. So we would expect the x values to grow. And then the x values are going to reach a maximum there when y is equal to pi over 2 and start to come back in. So yeah, this is a reasonable little picture here. Okay. We can verify with Desmos. But it's important that you go through that procedure of graphing these things by hand before. Oh, there it is. Okay, yeah, not bad at all, right? As y goes from 0 to pi, we get this picture. Here's ours. It's fine. And that wasn't hard, right? I didn't do any calculus. I didn't draw out any massive tables. I just thought a little bit about a few points that I knew were on the curve, and then the behavior of this function as a function of y. Now, I did mess up one thing. My axis of rotation needs to be way up here at 4. And I don't quite have room for that. So I'm going to fudge it in. I'm going to say this is the line y equals 4. 4 is certainly bigger than pi, right? And y equals a constant is always a horizontal line. So well, there should be a larger gap here. The This is still acceptable. Okay. So I think it's pretty clear what my region is. Someone's saying the shading wasn't dark enough the other day, so that's clear. There's my region. How do I draw the strip?
From the y-axis to any point on the curve.
Yeah, the strip should be oriented like this, right? Parallel to the axis of rotation. So I could put it in here anywhere, but it has to be oriented left to right like that. Let's put it in up here. It's always understood that this is at like a generic y value that we just call it y. And since the thickness of that strip is a dy thickness, I know that all the work I'm going to do is going to be done with respect to the variable y. Okay. What do I do next?
You can draw the cylinder, you can find the points on the graph.
Yeah, let's sketch the cylindrical shell. So if I rotate just this strip around this axis, I'll draw the cylinder as it would be oriented, which is like sideways. I could put it over here, but I don't have space. So I found out over the last few days that the whole family has COVID right now, which is not ideal. So my son protesting a little bit. He's not feeling good. Okay. So it doesn't have to be a work of art. But there is our little cylindrical shell. And he has a radius. And I use the word height, but you could call it a length if you want. I'll just keep using the symbol h. If I want to identify the radius and the height, I need to come back up here. This is h. And the distance from the strip to the axis of rotation is r. The solid of this little guy, I'm not going to draw the cut and unroll. You know what it looks like. You slice this thing and unroll it and you get a rectangular box. But I do want your help coming up with the value of the radius and the value of the height. So what is h?
Square root of sine y.
Very good, right? It's the x value here minus the x value here. The x value here is the square root of sine y, and the x value here is 0 because you're along the y-axis. So the height is the square root of the sine of y. And the radius? Radius here is maybe a little bit trickier. Who can help me out with that?
Would it be 4 minus square root of sine y?
Perfect. Oh, almost. Very close.
4
very close.
plus? No.
So slow down a little bit. You're on the right track. It's the vertical distance from here to here, right? So it's the y value here minus the y value here. You're correct that the y value up here is 4, but what is the y value here?
Square root of sine y.
Careful, that's the x value, right? X is equal to the square root of sine y. So allow me to sneak in here. I'm going to characterize this point right here. Where on the curve, x equals root sine y. So the x coordinate is root sine y. And y is the independent variable here. So the y coordinate we would just call y.
Gotcha.
So that distance, that vertical distance, the y value here minus the y value here is 4 minus y. Okay. And this stuff, this is the tricky part, right? For these problems, it's going to be 1 or 2 stats that are like a little bit hard to see. And that's why it's really important that you draw this picture and take your time, because if we just assume that one of these is like, oh, the thing that was given, or maybe it's just assume it's always X or assume it's always Y, you'll get into trouble real quick. And I will be writing the test questions to try and see if you can do this. So obviously this is the skill we're trying to come up with. Okay. So dV, the volume of my little cylindrical shell, is 2 pi r h dy, which is 2 pi times 4 minus y times the square root of the sine of y dy. Now we're almost ready. Let me take a quick look back at this problem. Just thinking ahead. So use another cylindrical shell to find the volume. Specified axis. All right. I have to think a little bit about this integral. Yeah, that would be worse. Okay. So then my volume V is always the integral of dV, in this case taken from down here to up here. That's going to be from y equals 0 up to y equals pi. Remember, it's a dy integral, so the bounds have to be y values. Just think about what's the smallest y value in my region, it's y equals 0. What's the largest y value in my region? It's y equals pi. We don't go all the way up to 4, right? Because the region stops right there at pi. So this is integral 0 to pi, 2 pi times 4 minus y times the square root of the sine of y dy. And to tell the truth, I don't see how to do this integral right away. It's not an easy one. Integrating the square root of sine y on its own is going to be a tricky biscuit. I'll have to think about this. There's only one thing that really makes sense to try, and that's subbing for sine y. Anything else is like inherently ludicrous. But this is rare. I've been teaching Calc 2 for years. Analysis is really my thing. And I don't think I've bumped into an integral during lecture that I don't immediately know what to do with since I was a grad student. So let's have fun with this. I'll pop out the 2 pi. Integrate from 0 to pi. 4 minus y times the square root of sine y.
Would it work if we do sine y to the power of 1 over 2 and then we distribute the 4 and the negative y? And then the exponent, oh no, it'd just be 3 over 2.
No, so the sine of y would be raised to the 1/2. So y to the 1 times sine of y all to the 1/2. You can't combine those powers. So the power here would be like, it would be like sine. I understand what you're asking, and I want to kind of be clear about this. So the square root of sine y, if you wanted to rewrite this as a power, it looks a little weird. You could rewrite it as the 1/2 power of sine y, or all of sine y to the 1/2, but it's not the same as sine of y to the 1/2 or anything like this. And we could not let this guy interact with this guy directly. That sine function is like a box, right? And the y cannot get into the box. So there really isn't anything we can do nicely algebra-wise here. You could distribute the 4 minus y, that's an option. So you'd have 4 times that square root minus y times that square root. But that doesn't appear to do anything nice for us. We may end up splitting it up in the end anyway. But my first thought was, perhaps we should think about using a different method here. But if you solve this for y, you get the inverse sine of x squared. And certainly that's not any easier to work with. And then also we would have to change our method, which would be quite tricky because this is not a one-to-one curve when we think of it as a function of x. So still left staring at this. Like I said, my only real thought here is maybe try subbing the sine of y. It's weird, but we can do it. Du would be cos y dy. That's going to be hard to figure out. And then this y is going to become a sine inverse of u. That's quite ugly as well. When y is equal to 0, u would be 0. When y is equal to pi, u would also be equal to 0. Yeah, something. So this is tricky. This is not at all obvious to me. We do have this set up. Stare at this for just a second longer. So this substitution is not going to do it. We could maybe try to exploit some symmetry, like find the volume that we get from just looking 0 to pi over 2. But that's not going to work either, because then doubling, that's not necessarily going to do the job. Let me table this for just a second. Let me see what I can get out of. Let's just try square root sine y first on its own. See if we get anything that looks manageable. No, definitely not. So what about y times the square root of sine y? These are hypergeometric functions. So something weird is going on here. We're not meant to evaluate this integral directly. Yeah, there is no nice closed form for this integral. This integral is a nightmare. So while the setup here is correct, this integral is impossible to evaluate by hand, which makes me question the approach we took. Where are we? This is from problem number 25. Oh, I thought these were the instructions for 25, but these are only for 15 through 20. Here we go, 21 through 26. Set up an integral for the solid obtained by rotating the region about the specified axis. Use your calculator to evaluate the integral correct to 5 decimal places. Yeah, okay. So this is not one we're meant to be able to evaluate by hand. All right, the textbook here tells us to use some sort of computer algebra system or calculator to evaluate the integral. So the setup was fun, and this is correct. But the actual computation of this integral is literally impossible. Not something you can do by hand. You can use a computer, which will use numerical methods. Even a good computer algebra system isn't going to give you a nice exact answer unless you're willing to take that answer in terms of these hypergeometric functions. And just to give you an idea how weird those are, I worked a lot with Q-basic hypergeometric functions. Regular hypergeometric functions aren't quite as bad, but here's the 2f1. It's a weird thing. It's a very weird thing. So at this point, they just want us to use a computer. Now, my favorite tool for crunching out nasty integrals like this, there are other things I'm sure you're aware of, like Symbolab and integral calculator and all that good shit, but Wolfram is really the best tool for numerically evaluating integrals. So I integral y squared sine y from 0 to 1 + 5. I shouldn't have said integrate and integral. I get confused. There we go, that's correct. All right. So we're looking at about 36.57. And this picture, of course, is not the same as the picture we have here, because that's the function they've drawn is this function, whereas the function we've drawn is just x equals square root sine y. So 36.6, let's call it. Okay. So good challenging problem. Let me warn you a little bit about something that's likely to show up on the test. I've been warning people about this for the last few semesters, and results have been interesting. Most of the volume problems that you can solve all the way by hand are a little bit boring. You've probably noticed that, right? Like the majority of the volume problems that you guys have looked at result in like exponential integrals or power rule integrals, which are not the most exciting thing in the world. But you can set up problems that are a little bit more challenging, and then issue or defer the actual evaluation of the integral to something like Wolfram. On the exam, I will require you set up a volume integral using both methods. I may ask you to evaluate one of them. I may tell you don't bother evaluating either of them. I may just work on the integration skills as a totally separate thing. You will need to sketch the curves, the region, the axis of rotation, draw the strip, and label distances. Label/find the relevant distances. You will not have a graphing calculator. No graphing utilities of any kind. On the test. So make sure you know your basic graphs. Things that have shown up include the natural log, and transformations. Like the ln of x plus 3 and so on. E to the x and transformations. Any trig function. And simple power functions. Power functions and simple polynomials. All right, you got to know these graphs. There's no excuse at this point in your mathematics career to not know these graphs. I used to walk through the exact problem using the natural log function that was going to be on the test in class multiple times, and I still had people butcher the graphs on the test. I'm not going to do that this time. I'm not going to walk you through the exact problem that will be on the test, but I'll tell you it'll be, something like this. So please know how to graph functions by hand. I had no idea what x equals the square root of sine y looked like, but we got a really good picture there just by thinking of a few points and asking what does this function do as y increases from 0 to pi. But that's really all it takes, but you got to have those skills. And if you cheat, I'll know. If I catch you cheating, I will fry your ass so hard it will make your head spin. Please don't do that. I gave you my spiel on cheating on the first day. I don't want to go back through all of that. So here's the stuff you need in order to not panic or get caught out on the test. When it comes to graphing. Sorry, our dog has learned how to open doors. Okay, so that's it for volumes. We do need to talk a little bit about work. So I'm going to keep this simple. I'm going to give you two definitions of work. Work is a force applied over a distance. That's one definition. Or you could say work. Sorry, how to do this. So work is a use of energy. And each of these words has a particular meaning in physics. So energy is sometimes defined as the ability to do work. That if I left that as the definition, it would be circular. The definition that's more useful for us is a force applied over a distance. The definition that's in your textbook is, here we go. Oh, this is bad. Usually we would call this the force function, and we would do the integral dl, thinking of this as a length. So the function f that they're thinking of here is measuring your force. It's the force that you're applying at position x, and then x is your position. So you're integrating over a distance. So we'll grab out the important parts. If you're moving an object along the x-axis from x equals a to x equals b, and you're applying a force F at every position x along that way, then you can think of f of x as your force, and then your work really is just the integral of the force over that distance. So in calculus terms, if we are moving an object along the x-axis by applying the force F of X, and that's at each position X, then the work done moving the object from position X equals A to position X equals B is, and you can take this to be your definition for our class. In physics, you'll usually see a capital F here, and then your differential is usually dl. It's like a little length. Oh, answer to the question in chat there after ln x, what was written, said and transformations, shifted versions of that function. So here's the picture. I've got my object here, and it's at position X, and I'm pushing on it or pulling on it with force F. At that position. So the object starts over here, and at every position X between A and B, I'm applying the force little f. That force might change depending on where we are. And in order to calculate the work that's done moving the object all the way here to all the way over here, you do this integral. In physics, you'll see this written as integral of f dot dl. And the integral would usually be done with respect to time in physics. So dl is going to be some little length times a little time, and both of these would be vectors. But for us, we can just take it to be this. First thing to notice, if your force is constant, if you're pushing with a constant force, then you really don't need this integral because you're just integrating a constant. So let's call this an example. If I push a box along the floor with a force of 2 newtons from my desk to under the bed 3 meters away. How much work do I do? There are some questions like this in the textbook that are meant to kind of catch you out with their simplicity. But the idea here is that my force is constant. I'm always pushing with 2 newtons of force. So if you kind of think of it, maybe here's the desk. Over here's the bed. Here's my box. And I'm pushing on this thing with a force of 2 newtons. I'll say the desk is at 0 meters and the bed is at 3 meters. So one of the challenges with physics problems is that you have to come up with your coordinate system. It's not given to you. But I'm always using the exact same force. So right here at 0.8 meters, I'm applying 2 newtons. Right here at 1.5 meters, I'm still applying 2 newtons. As I arrive at the bed, I'm still applying 2 newtons. The force is constant. So you could say, all right, the work is going to be the integral from 0 to 3, right? From my starting position to my ending position of this function dx. I'm leaving the units in there. You could leave the n for newtons off if you want, but that's a constant. So that's 2 newtons times the integral from 0 to 3 of dx. And distance here, remember, is being measured in meters. So that's 2 newtons times the integral of dx is just x. So this would be 3 meters, which is 6 Newton meters. And that's the unit that you have for work. The SI unit is Newton meters, which is AKA joules, which you notice is the same unit as energy if you've taken physics. So work and energy are kind of equivalent. And there's an important theorem in physics called the work-energy theorem that relates them. All right. So the big take home is if your force is constant, then you really don't need to do an integral, just multiply the force by the distance, right? That's what we ended up doing here. And that's what the textbook's little discussion at the start is. Questions on this example or the definition of work? All right, then I have a fun question for you. What if there's a spring over here? There's a spring attached to my bed and the box that I have to compress as I push the box towards the bed. I know that's not a very realistic situation, but what if the force I have to use to move the box changes with the position? Because that's precisely what a spring does.
You gotta increase the force
Right, yeah.
by a value of X.
Spring, yeah, what Daniel said is exactly correct. As I move the box, I compress the spring. And that means to take each additional step towards the bed, I need to use more and more force. There is a rule that
we would use 2 newtons X.
Something like that, something like that. So in order to get into this, we have to talk about what's called Hooke's law. Again, more physics. I'm not a physicist, but I'm happy to share a little bit with you. Hooke's law says, very simply, the force required to stretch or compress a spring is proportional to the distance you compress, stretch, or compress the spring. All right, so every spring has a sort of natural equilibrium state. You're just holding the spring, you're not pushing it or stretching it. If you want to compress it from that equilibrium state, or you want to stretch it from that equilibrium state, you have to press harder and harder and harder and harder as you compress the spring more. And the amount that you have to push harder and harder by is proportional to how far you're pushing. In mathematics notation here, we would say the force is equal to some constant times the distance that you're compressing, x. F here is the force required. X is the distance from equilibrium. And K is called the spring constant. Which changes from spring to spring, right? Some springs, like if I take the valve spring off of my cars, The head, the cylinder head in my car, those are incredibly strong springs. They have a very, very large spring constant. They're very, very hard to press. On the other hand, if I take like the plastic slinky, that's very, very easy to stretch and compress. So that has a very, very small spring constant. But this is Hooke's law. Let's look at a problem. All right, you see here a nice picture, right? So I've got, you imagine that I've got some object here attached to a spring, the surface has no friction, sure. This is the thing at rest in equilibrium. And if I want to stretch or compress that spring by a distance of x, then the force that's required is equal to some constant times that distance. And that constant is called the spring constant. This is Hooke's law. All right. So they say here a force of 40 newtons is required to hold a spring that's been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 to 18 centimeters? Let me write down the important stuff and then we'll work on it. So we do a force of 40 newtons is required to hold spring, to hold a 10 cm spring out at 15 centimeters. How much work is done? Stretching that spring from 15 to 18. All right. One thing you have to be a little bit careful with here is that when we're working with physics stuff, units really do matter. And the SI unit here is Newton meters. All of our distances are given to us in centimeters. So we would want to write each of these distances in meters as we work. And we need to find the spring constant for this spring, right? I wasn't given the spring constant. That's kind of the catch. So your starting steps for these would be to find the spring constant, then set up your integral. I think it's wise to draw the picture. Or perhaps not necessary. So in order to stretch my spring from its equilibrium, which is 10 centimeters, where it wants to be, which I'll call x equals 0, out to 15 centimeters, which would be here. We'll have to in order to kind of hold this guy here, I have to be pulling with a force of 40 newtons. So to go from here to here, the force required to hold that is 40 newtons. And we want to know how hard or how much work do I have to do to continue stretching this all the way up to 18 centimeters. So first, find the spring constant. Ten centimeters is 0.1 meters. And 15 centimeters is 0.15 meters. So this would be, I'll call this x equals 0 meters, and I'll call this x equals 0.05 meters. Now, no. All right, because we want to work in SI units. We want to work in the regular units for work, which are Newton meters. So the displacement from here to here is 0.05 meters. We know that the force is equal to K times X. The force there is 40 newtons. And that's equal to K times the distance that I had to stretch here, which is from 0 meters to 0.05 meters. And if you divide both sides by 0.05, little foot on space there over here, you'll find that K is 40 newtons divided by 0.05 meters. So the units here are newtons over meters. And 0.05, that's 5 over 100. So this is 40 divided by 5 over 100 newtons over meters. So let's see, what is 40 divided by 5? That's 8. And 8 times 100 is 800. So that's my spring constant. So K is 800. And again, wise to keep track of the units, but not necessary. So my force, the force I need to stretch or compress this spring by a distance of x from its equilibrium, which is 10 centimeters, is 800 x. And the units here, 800 has units of newtons per meter. X has the units of meters, so the units here would be newtons, the unit of force. And then the question is, well, what do I have, how much work is done to stretch that spring from 15 to 18 centimeters? Well, here's 18 centimeters, I'll exaggerate it a little bit. And that would be x equals 0.08 meters, right? Because remember, my equilibrium is the 0 position. So I want to integrate from 0.05 out to 0.08. That's my aim, is to further stretch this spring out to here. So once you've got this, now you can set up your integral. Or would be the integral from the position A to the position B of your force function, which f of x dx. F of x is your force.
You move up
A
the
and B are your starting
camera,
and
please.
ending positions. Oh, sorry, yeah, let me move this up. So remember, f of x, this is your force, the force you have to apply at distance x, and A and B are your starting and ending positions. So I'm starting here, 15 centimeters out from the wall, which is 0.05 meters from the equilibrium. And I want to come out to 0.08 meters from my equilibrium. And the force I need to apply is 800 x. And this is measured in newtons. I'm going to leave the units off here inside the integral. But this is your force. So you do the antiderivative, you calculate an antiderivative here. Antiderivative for x is 1/2 x squared. So this is going to be 400 x squared evaluated from 0.05 out to 0.08. And then you're going to have to do a little bit of gnarly arithmetic here, but we can do that. And pop the 400 out. And this would be 0.08 squared minus 0.05 squared. Neither of which are nice. I guess I would probably write both as fractions. So 0.08, that's 8 over 100 squared minus 0.05 is 5 over 100 squared. That's 400 over 100 squared times 64 minus 25. I'm factoring out the 100 squared from the bottom. So 100 squared, that's 10 squared squared, or 10 to the 4 is 10,000. And then here, 64 minus 25 is easy to compute. That's 8 squared minus 5 squared. So what is that? That's, let's see, 25 plus 40 would be 65. So this is 39. And then 400 divided by 100 squared is 400 divided by 10,000. So we can definitely cancel a factor of 100 there, right? So that's 4 over 100 times 64 minus 25. I think we said that's 39, right? And then the 4 over 100, you can clean that up a little bit too. If you divide top and bottom by, oh, this is divisible by 4 also, isn't it? Yeah, so that's 39 over 25. And the units here would be Newton meters. Not too bad, right? Hooke's law and these basic things were like you're either, gorilla pushing something up a tree or you're sliding a box across the floor. Those are the hardest work problems I'll give you. I'll say right here and very clearly, this is not a physics class. I am not here to teach you physics. I'm here to teach you calculus. All this shit, everything up to, literally up to this step right here is physics. That's not what this class is about, but I'm required to show you some applications. So we're getting this in here. Hooke's law is important. When you take differential equations, which I'm assuming you will, but you may not, if you take differential equations, one of the most important physical systems to kind of try to understand is what's called a damped harmonic oscillator, which is where you have some mass attached to the end of your spring here, and it's allowed to slide back and forth. And then on this side, you have one of those dash pots. I don't know if you know what I'm talking about, like on a door, when you try to slam a door at the 7-Eleven, not that you should ever do that, it won't let you. There's a little dampener there. So if you have a spring attached to a mass, attached to a dash pot, that creates a system called a damped harmonic oscillator. Just the spring and the mass would be a harmonic oscillator. If I stretch this out and then let it go, then the box would bounce back and forth and back and forth and back and forth and back and forth, just like a sine wave or a cosine wave. If you attach the dash pot over here, that dampener, then it'll be pulled back, but it'll slow down and then those sort of systems are very important kind of prototypes for understanding more complicated physical systems. So Hooke's law, this little bit of work is actually worth your time, even though it's really not mathematics, it's physics. Questions on this problem? Okay, that's really all I have to say about work. Let's see where we're at time-wise. Why isn't this showing up? Oh, there it is, 10:49. Okay, we're right on time too, right? 9:30 to 10:45 is where we're supposed to end. So this is perfect. Next Monday, we are going to begin talking about methods of integration. All right, we're done with the easy stuff. This first few bits of Calc 2 are applications of the integral, kind of giving you time to remember all the stuff from Calc 1 that you're supposed to remember, while at the same time doing some geometry and physics. Starting next week, we're doing the real stuff. And the real stuff is methods of integration and then sequences and series. That's the bulk of this class. So next week, we need to have our big boy pants on. We need to start working really, really hard. Please make sure you're caught up with the homework by Monday. That's critical. You cannot be behind at this stage of the course. On Monday, I'm going to show you integration by parts.
Monday's
Backwards.
called?
Oh shit, it's a holiday. Yeah, okay, Wednesday. Wednesday, I'm going to show you integration by parts, which is the backwards product rule. It's like a product rule for integrals. After that, we're going to start talking about trig integrals and then trigonometric substitutions and then partial fractions, and then we'll be coming up on the tests. So let me just show you really quickly here. IBP, trig integrals, that's next week. Okay, both of these are hard sections. 7.1 and 7.2 are integration by parts and trigonometric integrals respectively. Integration by parts, like I said, backwards product rule. Trig integrals, most of this section is about knowing your trig identities and being really comfortable with them. So please study up on your trig identities. All three forms of the Pythagorean identity, sine squared plus cos squared equals 1, tan squared plus 1 equals secant squared, 1 plus cotangent squared equals cosecant squared, and also your half angle identities, cos squared theta equals 1/2 1 plus cos 2 theta, and sine squared theta equals 1/2 1 minus cos 2 theta. You need those identities for this section. And then the rest of it's U sub, really. Like we use those identities and we use U sub here. Integration by parts, though, this is a trickier whole new thing. So we'll spend all of Wednesday and maybe some of Friday on this, definitely Friday on this. I might post a little primer because we're not going to get to meet on Monday. After that is trig sub. This is another hard section. This is where you're given an algebraic integral, an integral with like, you know, x's and x squareds and square roots and stuff. And the way you solve it is by subbing in a trig function. So they don't have trig in them to begin with. You introduce the trig through a substitution, and then you use the methods of 7.2 to solve the resulting integral. This is a very important section. Many, many integrals that are impossible for us right now will become possible through this method. And then partial fractions, this is something we used to teach in pre-calculus. It's a purely algebra process that you use to split complicated rational functions, ratios of polynomials, into simpler rational functions. This is also something that folks tend to have a little bit of a hard time with. So all these sections that are coming up, they're tricky. So be ready to really, really work. And after we finish partial fractions, we're going to get ready for test 1. So as soon as we finish section 7.4, I will release your study guide the following week. We will cover 7.5, which is like a summary of integration technique and strategies. And then at the end of that week, we will have our first test. All right, so if you're thinking ahead, I would say exam 1 is probably around the 24th. And you really need to knuckle down and get ready for this. These first few sections, they're easy. These are not easy, so be ready. All right, if you need anything from me, you can come see me in office hours, send me a Canvas message, talk on the Discord, all that stuff. I don't know if our class's Discord link is expired right now, but I'll be posting a fresh one. I'll try to update that as every so often in case because it does expire once a week. Please communicate with me if you're in trouble, if you're worried, anything like that. Talk to me sooner the better. So if you know your trig identities are rough, come see me today and I'll get you some stuff to practice them. If you know you have trouble with partial fractions or algebra or whatever, come see me today. I'll get you stuff to get ready for it. But we got to be ready. All right. That's it for me. I hope you guys have a lovely rest of your day, and I will see you all on Wednesday of next week.